Okay, so here's your function sine square root of sine x. It's these little bit of kind of look like semicircles, but they're not quite semicircles. Okay. Obviously, you've got nothing defined here because at this stage sine would be negative and the square root doesn't exist. So it exists only between 0 to pi. Let's go back to what our instructions are. Okay. Draw a diagram, write the volume as an integral. So first we're going to do a representative rectangle and its volume. So let's go do that. So here's your representative rectangle. Okay, its height is going to be fx. Okay, our radius is fx, width is delta x. So the representative volume is going to be pi fx quantity squared dx. You're going to integrate this, okay, and you're going to go from 0 to pi as your limits for integration. So then this becomes pi integral 0 to pi sine x dx, and you integrate this, you know you should get minus cosine x from pi to 0, which is equal to pi minus cosine pi plus cosine 0. And you should know that cosine pi is negative 1, so then this becomes 1, cosine of 0 is 1, so your volume is equal to 2 pi, whatever the units are for x, okay? 2 pi cubic, whatever. Right, let's see if I actually work this entire example out, or did I just put an integral there. Oh, I like that Nike. Okay, so I guess I didn't work the whole thing out. All I have is set up the integral, and I showed you what the answer is. So let's go back there. It's 2 pi. Okay. So one more time, the technique is very similar, is the same as what we've done before. Draw the graph, create a representative rectangle, generate a representative volume, put it under the integral, then just do it. Right, do I have yet another example to go through? Okay, let me pause here and recapture my thoughts. All right, so the next example is obtaining the volume of a solid of revolution when the rotation is not about the x-axis. It turns out that really the disk method is meant for generating volume of a solid whereby the axis of rotation is going to be adjacent to the area that you are actually rotating. Okay, so you're rotating the graph 2 minus x squared about the line gx equals 1, i.e. y equals 1. Okay, so the first thing you obviously need to do is graph that, and here's the region. Okay, so we're going to be generating a volume by rotating the shaded region. Okay, the shaded region here. Okay, about this axis here. About this axis here. Okay, instead of the x-axis. So the ideas are very similar. Obviously, what we need to know is we need to know the limits of integration. So we need to know that point and that point. Okay. And you can get that by setting these to equal and solving. Okay, so x equals plus or minus 1, as you can see it on the graph. So your representative volume is going to be pi. Your radius is fx minus gx quantity squared. Your height is dx, delta x. You're going to integrate from minus 1 to 1. Okay, which then becomes equal to pi minus 1 to 1. Fx minus gx is going to be 2 minus x squared minus 1. You need to square this thing. Okay, and then just do it. So let's just do it. Minus 1 to 1. This guy becomes 1 minus x squared quantity squared dx, which then becomes equal to pi integrate minus 1 to 1. 1 minus 2x squared plus x to the 4th dx. One thing I want to bring out is that notice that there's no sloppiness here. Notice that I don't drop this, like many of you have done in the test that I just graded a little while ago. Okay, notice that I don't drop these. Okay, I don't drop these, okay, which many of you again tend to do, and you bring them in towards the end. That is nothing more than slop. Okay, don't do that. Right, just do it. You get pi x minus 2 over 3 x cubed plus x to the 5 over 5 from 1 to minus 1, and then bring it out here and plug and chug. So you get pi, so volume equals pi. Put in 1, so you get 1 minus 2 over 3 plus 1 over 5 minus, putting in negative 1, get minus 1 plus 2 over 3 and minus 1 over 5. Okay, so are things cancelling out here? Not really. So this becomes pi. It looks like it's kind of symmetric, isn't it? Yeah, kind of makes sense because it's a square. So I would have gotten 2 out of here. Okay, so that gives me a 2. This is a minus 2/3 and a minus 2/3, so that's a minus 4/3, and then it's a plus 1/5 and plus 1/5, that's plus 2/5. Doing the arithmetic becomes common denominator is 15, so that would be 30 minus 20 plus 6, and that gives me 10, 16 over 15 pi cubic units, whatever the dimensions are. Did I do this whole example, and do I have an answer somewhere? Okay, I guess I didn't show the answer. Let me see if I can find it somewhere. So I'll pause this for a minute and see where I got this example from. I'm sure it's from the book somewhere. So let me pause this. Right, so really this is what I just did was example 2 from your book. And so the answer is indeed 16 over 15 pi right there. Okay, so got that right. All right, so here's a summary for how you do the volume of a solid of revolution by the disk method. So far we've been kind of doing it by rotating something about the x-axis or something that's parallel to the x-axis. So a representative rectangle is vertical. We're always integrating with respect to 2x. In 7.2b, I'm going to be doing it with respect to the y variable, and our representative rectangle, hence the volume, would be horizontal. Okay, would be horizontal. So your steps are: you draw a diagram, formulate the volume of a disk, put it underneath a rectangle, and then just integrate it. Then just do it. Okay. All right. So this is 7.2a.